Welcome to Ready to Derive. In this video, we're going to learn about the concept of the average value of a function. Now, we all know we've met averages before. So for example, if you get, let's have a look at this. If you were to have three test scores, 75, 80, and 85, and you were to work out the average of those three test scores, we all know that we add them up and then divide by 3. So that's 240 divided by 3. And our average is 80, which we could have probably figured out by just looking at the symmetry. But what does an average of 80 actually mean? How else could we have got an average of 80? Well, you could have just got 76, 80, and 84, right? That would give the same average. In that case, could we not also say that we got 80, 80, and 80 on each of the three? It's as if we did. So averaging out something is sort of like smoothing out to make it consistent along the way. But what does it mean to have the average value of a function? This example of 3 test scores is easy enough. Even 10 test scores would be manageable. But a function is continuous and has infinitely many values. So how do we find the average of infinitely many values? Well, stay tuned. That's what we're about to do. So let's begin with an everyday scenario regarding average temperature, just to make the concept more concrete. So suppose you record the temperature in Celsius once every hour between 6 a.m. and 6 p.m. Find the average temperature over the time interval. And here are the temperatures. So our first observation is at 7 degrees Celsius, and then after the 12th hour, it's 19 degrees Celsius, and it fluctuates over that interval. So we know that the average temperature, if we have a discrete number of observations, we would just take the total, we would add up the y column, that y1 column, and that comes out to 204.5. We divide by the number of observations, 12, and that comes out to be, like I said, this is approximately 17 degrees Celsius. So this is very easy to do, and if we made more observations, we would calculate the average temperature in the same way. Now let's have a look at these. These are the observations graphed. You can see that they kind of make a very nice looking smooth curve. What we're really doing is we're adding up these 12 y values, I won't shade them all, and then dividing by 12 to get the average temperature. And it seems like the average temperature of 17 degrees Celsius is, let's see, it's around 17, this is 12, 14, 16, it's about here, okay, just using those observations. But what if we could actually describe the temperature at any point during the day with a function? And here is a function I created that now it might surprise you, it goes through all the data points. Well, that's because I made the function up and then created the data values based on that function. But how would we find the average temperature? Like, and I have that in quotes, average temperature, because that would be the true average temperature for the day. How might we do that? Well, we don't want to sit there recording. I mean, technically, you could just do lots of observations, which would be recording the temperature at every moment, every millisecond. But if we can see that actually, if we want all those observations added up, that's really just finding the area under a curve. So if we took that red area, would be the area from 0 to 12 under the function, under our temperature function. But we know that we actually have to, if we're doing averages, we have to divide that by something. So this is sort of giving you an idea of where the formula comes from that you'll meet in a moment, but this is hopefully giving you an intuitive idea. You actually divide by the time interval that's elapsed, which is 12 minus 0, right, which is just 1/12. So like just for now, you have to trust the process. That area under the curve comes out to be, I did it with a calculator, 198.02. And then if we divide that by 12, we get 16.5 degrees Celsius, which is, so that is the true average temperature for the day. If we have a look at that, we can see it's very close to 17 degrees, but that would be the average temperature if you are considering temperature to be a continuous function, which indeed it is, and if, of course, you had a formula to measure it. So let's just formalize the definition of an average value of a function over a closed interval. As we saw in the previous example, to find the average value of the function, we do 1 over b minus a times the integral from a to b of f of x dx. And now, so what does that mean exactly? So here we have a function defined over the interval, let's call that a, b. And if we calculate, we do this calculation, which we will practice momentarily, we're going to get an average value. So if we followed that along and read that y-coordinate off, that would be f average. And there's a real nice geometric interpretation of this. So let's just do a little rearranging, see what's so special about the average value. If we multiply b minus a to the other side, I'm going to keep this in green, color coordinate it. We see that we, on the right-hand side, we get isolated, we get left with the integral. And that integral in red is just the area under the curve, under the function. But the calculations on the left, f average times b minus a, now have a look at that. F average is this height, and b minus a is this distance. And if you multiply those together, you basically get the area of a rectangle. So it turns out that what the average value does is it essentially allows us to kind of redistribute the area under the function evenly over the interval a, b. And so that's kind of pretty neat, and we'll explore this more a little later. But what's very cool about it is it also, if those areas, if the red area is indeed equal to the area of the rectangle, then if we take this little area that's jutting out here and we rearrange it, it should fit perfectly, or the value of the area is exactly equal to what's missing here, because obviously the red area has to end up being equal to the area of the rectangle. So for our first practice problem, I'm going to find the average value of cosine 2x over the interval 0 to pi over 4. So let's call up the formula. The upper limit b is pi over 4, the lower limit a is 0. So 0 to pi over 4 cosine 2x dx. And pi over 4, 1 over pi over 4 is going to become 4 over pi. And the antiderivative cosine 2x. Now you could do u substitution. Well, you would do u substitution and call this u is 2x and continue from there. But you can also kind of use common sense here. The antiderivative cosine 2x must be sine 2x, but the derivative of sine 2x would give 2 cosine 2x, which is not what we want. So we have to put a half there to compensate. Again, you can achieve that through u substitution if you prefer. I'm going to pull this half out here. I like to pull any constants out before I start substituting in. So I have 2 over pi out there, and then sine of 2 pi over 4 minus sine of 2 times 0, which is 0. And that will be 2 over pi. The sine of 2 pi over 4 is sine of pi over 2, which is 1. Sine of 0 is 0. And so the final answer is just 2 over pi. And let's have a look at that visually. So here is the function in red. And this in green, we have the average value, which is 2 over pi. And just to reinforce the concepts regarding area, that means that the area under the curve, f of x, that area, which is given by this integral, remember? So the area under that curve is equivalent to the area of the rectangle whose height is 2 over pi and whose base extends from 0 to pi over 4. So let's do another practice problem. The function 3 over x plus 2 over the interval -1 to 1. And let's just plug in. So we have 1 over 1 minus -1, the integral from -1 to 1 of 3 over x plus 2 dx. And 1 over that would be 2 in the denominator. And again, I'm going to pull out the constants. I'm going to pull 3 outside there just to make the math a little easier. Actually, well, you know what? I'll just write this again, just to be sure we're on the same page. All right, and now we'll do that antiderivative. Fortunately, the antiderivative of we don't really have to use substitution, because we know the antiderivative of 1 over x, or x plus anything, is going to be ln. And the derivative, though, what we can check, does the derivative of ln x plus 2 get us back to here? It does, because the chain rule, the derivative of the inside function of x plus 2 is just 1. So there's no complications here. And then we would get 3/2, and ln of 1 plus 2 is 3. We don't need the absolute value anymore. Ln of, let's just check, -1 plus 2 is 1. Okay, so that's going to give that. Ln of 1 is 0, so we get 3/2 ln 3. This time I'm going to circle, let's see, circle the answer in green, because that's how we're going to represent the average value. So here we go. The average value, 3 over 2 ln 3. That's this y value here. And once again, the area under the function between -1 and 1 will be equivalent to the area of the rectangle, whose height is 3/2 ln 3 and whose base extends from -1 to 1. So for our third practice problem, let's do a contextual problem. We're going to find the average velocity of a particle over the time period 0 to 12, and the velocity function is given. So I'm going to adapt the formula to apply to the context. We're dealing with time, so t2 is 12 minus t1 is 0, sorry, 0 to 12 of 3 minus a half t dt. And so that's 1/12, and the antiderivative is 3t minus, let's see, a quarter t squared from 0 to 12. That's 1/12. 3 times 12 minus a quarter, 12 squared, minus, luckily when we put 0 in there, we just get 0. We get 1/12. 36 minus 36. So we actually get a final answer of 0. So let me just put VAV equals 0. What does it mean for its average velocity to be 0? Well, let's take a look. So you might not have sort of thought about this ahead of time, but we have that the velocity is a linear function. And if we graph the average value, of course it comes along at 0. Maybe we could have predicted that by seeing that think about it, what is the area under the function? It would be this area, which would be positive, plus this area all the way to 12, which would, since it's congruent, would be the negative version of that. They would cancel out. So the area under the curve, or under the line from 0 to 12, would be 0. And so, of course, the average value is 0. And so, well, while you can't build a rectangle with area 0, so there's no rectangle to be shown there, it makes sense, because if the area under the curve is 0, then the rectangle must have 0 area. I'd like to briefly talk about the velocity function we were just looking at. When we worked out the average, we did it with the fancy integral formula. But if we thought about it, if we know that the initial velocity is 3 and the final velocity is -3, we could have just taken the arithmetic mean of those two values. So for a linear function, you can find the average value of the function by just taking the arithmetic mean of the function values at the endpoints. But what about for a concave down function? So let me use a different color, and let me just create over the same interval with the same endpoints, concave down function. Now, because every y value along that blue concave down function is higher than along the linear, the red function, we can predict that the average value has to be higher and than the arithmetic average, and that is true. So for a concave down function, this holds true. And let's also consider a concave up function. So if instead our function along here was concave up, that means the y values on the purple function are systematically less than that on the red. So we know that the average value will have to be below the one for the linear function. So this is always true for a concave up function. So just an interesting aside. but let's move on. So for our fourth practice problem, we're going to do a couple parts of the AP Calc 2019 free response question 1 exam. So fish are entering a lake at a rate given by ET and leaving at a rate given by LT, both of which are measured in fish per hour. So the first part A of this question asks how many fish enter the lake over the 5-hour time period. Notice there's no mention of average here. We're not talking about, for a moment, we're just going to step aside and just go back to our basic understanding. So the number of fish, you should recall, is given by the area under the rate curve. So this rate curve is ET from 0 to 5, because that will give us the amount of fish that have accumulated over that time period. Now, you don't actually have to write out ET in its entirety. You don't have to write 20 plus 15 sine pi over 6t. You can just write it like this. This is a calculator active question, and so I did this on the calculator, and it comes out to, now because this is number of fish, you want to make sure you round, so 153, around 153 whole fish enter during that time period. Now part B is, what is the average number of fish that leave the lake per hour over the same 5-hour time period? So it's the average number of fish per hour. So what we're actually working out is the leaving, let's give it a little code, so the rate at which they're leaving average over that time period. And now we know that the formula is 1 over 5 minus 0, the integral. Now we are taking the integral of the leave curve, the definite integral from 0 to 5. And again, we do this on the calculator, and it comes out to be 6.05. And because this is, let's see, 3 decimal places, 6.059. Because this is an average, it can be a decimal. We don't have to round, but let's make sure we get the correct rate. So it's not the average number of fish, it's the average number of fish that leave the lake per hour. We won't do part C and D because they're not as pertinent to this subject matter. So a study of average value of a function would not be complete without introducing the mean value theorem for integrals. And much like the mean value theorem for derivatives we learned earlier in the course, this says that if f is continuous on the interval ab, then there exists a number c in the interval ab. There could be more than one, but there's at least one, such that f of c equals the average value of the function. So let's take a look at that visually. What are we saying here? So we're saying that, let's see, this, if we follow this along, we're saying this is f av, but we also now are saying it must be the value of a function at a certain number c. And if we follow this along, so if we come along here to where it intersects the curve, then we see, oh, pardon the use of all the c's, that there is one point, there is only one point in this case, but there could be more. There is one value in the interval a to b, it's guaranteed to be in that interval, that corresponds to f of c. And so, what another way of looking at this, we're going to make the area connection again. So let's take, hold on a minute, let's kind of try and be color coded. We're going to take b minus a, we're going to cross multiply as we did before, and that product has to equal the integral from a to b of f of x. And what is that? That is just the area under the function between a and b. And so, that's the right-hand side, and the left-hand side, of course, is the area of the rectangle, whose height is fc, which is the same as f av, times b minus a. So we are going to, and let's just formalize this one more time. So there is a number c in the interval ab such that the rectangle with base ab and height fc has area equal to that under f from a to b. So it takes it just one step further. It's this existence theorem. It guarantees the existence of at least one c. We'll practice this in the next slide. So for our last practice problem, we'll just end up with an example where we try and find c. So let's go through this. So f av, the average value of the function over the interval 2 to 5. So 5 minus 2 from 2 to 5, x minus 3 squared dx, and that's 1/3. And now we could FOIL x minus 3 squared out and take the antiderivative that way, but it's a little easier just to treat it as a whole. It must have come from x minus 3 cubed, but when you take the derivative of that, you'd get an extra 3 you don't want, so you need to compensate by multiplying by 1/3. You could also do that using substitution. And that I'm going to bring that 1/3 out for simplicity, so it becomes 1/9. And then if we work this out, we have 5 minus 3 cubed minus 2 minus 3 cubed. If you work all that out, it actually comes out to be 1. So that's our average value. And now, so this next step about finding this C value. So here, we know that it must take on the average value of 1 at some point. So all we do now is we say, well, let's find out when x minus 3 squared equals 1. Because we want f of, this is really just a y value, or it's an f value. So we solve this, and if we solve this, we get x minus 3 equals plus or minus 1. And if we consider the two cases, well, either x will be 4, or the other one, x will be 2. So you can solve those to find those out. So there's actually, now there's two values of c. So let's take a look at this. Let's take a look at the graph. Because so here's the graph of f, and now we are going to construct the rectangle whose area is the same as the area under the graph of f. So remember, the average value was 1. So if we follow it along, oh look, there we go. So we have one c value at 2, but if we follow it along even further, we have another c value at 4. And if we want to, we know that the height of this rectangle is 1, and we know that, let's follow this along because we're going to 5. So here is the rectangle shaded in that has the same area as the area under the graph of f over that interval. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.